Hi everyone. In this section we'll be looking at probability and also conditional probability. Same as before, let's look at the outcomes first. First thing is know the definitions, very important. Then you must be able to estimate probabilities using relative frequencies, which was done in the section on frequency distributions. Next, you must be able to calculate probabilities using basic operations, calculate probability using counting techniques, and calculate probabilities from word problems. Very important because that's the type of problems that you'll be getting in the test and the exam. Right, now just a reminder, statements regarding things like the weather, the chances of getting a specific outcome when you roll a die or flipping a coin, those are attempts at quantifying uncertainty, and in order to do that we need to have a random experiment. The outcomes will be uncertain, however they must be well defined. In other words, we must be able to list all possible outcomes. Right, that's really important. We must be able to list all possible outcomes. Right, let's consider the example on rolling a six-sided die. So we have our sample space, which consists of the outcomes 1 up to 6. And on here I've defined 3 events. Events O will be the event of odd numbers, 1, 3, and 5. Event A will be the event of the first 3 numbers, 1, 2, and 3. And event E will be the event of even numbers, 2, 4, and 6. Over here, sample space for a 20-sided die. Those of you who've played D&D, you will know what a 20-sided die looks like. It looks basically like a soccer ball for those who don't. So here we have a sample space, and it has 20 outcomes, and we have also event A on here, which consists of the first 3 numbers, 1, 2, and 3. Now if we look at the frequency of event A, then it is equal to 3 in both of these cases. However, if we look at the entire sample space, then we see that event A is not exactly the same for both, even though the frequency is 3 and it contains the first 3 outcomes, 1, 2, and 3. So if we look at what we call the relative size of event A, right, the relative size of event A, then we see that the relative size compared to the sample space is 3 over 6, which is a half, 0.5. The relative size of A compared to the sample space for sample space 2 is 3 over 20, which is 0.15. So where this one is 0.5, this one is 0.15. So clearly the size of event A is very different when we compare between the two sample spaces. So what we can see as well is that just knowing the frequency of an event is not good enough, because it doesn't exactly give all the information regarding that event. So we prefer to work with the relative size. Right, now the relative size we'll refer to as, if you look over here, the relative size we'll refer to as the relative frequency of A when we work with a sample, and the relative size we'll refer to as the probability of A when we work with a population. Same over here, relative frequency of A will be used to measure the relative size for a sample, and the probability will be used to measure the size for a population. Right, so if we look at what I just showed you, then you'll see that probability is just a numerical measure that measures the likelihood of something. Okay, what are the chances of something happening? Of course, if the event has a chance that is close to 0, it means that it's not likely to happen. If it is close to 1, then it will almost certain happen. And of course, if it is 0, then it's definitely not going to happen. And if it is 1, then it is certainly going to happen. And we can see over here, rolling a 6-sided die, the chance of getting one of the first 3 numbers is 0.5. Whereas over here, the chance of rolling one of the first 3 numbers is 0.15. Right, now there's 3 ways that we can assign probabilities. The first one is the classical method or principle of indifference. That simply means that we treat all the outcomes the same. The next one is the relative frequency method, which means that we perform an experiment and we get a sample space and then we count. And the last one is subjective method, which is assigning probabilities based on prior knowledge or experience. Now, for our purposes, we'll only be looking at the first 2, classical method and the relative frequency method. Right, now I'm going to compare them side by side so that you can actually see what happens. Now, classical method, as I said, we treat all outcomes as equal, so we have equally likely outcomes. So that means the probability of a specific outcome will be 1 over n if the sample size is n. Now, please note that this lowercase n refers to a sample, but it will be valid for a population as well. Right, the relative frequency method, we'll either have an experiment or historical data, and that means we're estimating probabilities. Okay, if you think about what I said a moment ago, relative frequencies, those are the relative sizes of events when we work with samples. Probability, that's the relative size when we work with populations. So when we work with populations, we get the true values. When we work with samples, we get estimates. So relative frequency is an estimate of a probability. Now let's consider our 6-sided die. Then the probability of getting the number 1, according to the classical method, will be the same as number 2, number 3, all the way to 6, and that's going to be 1 over 6. So we are saying that we're working with a fair die over here. Okay, a fair die or a balanced die, because all outcomes have the same chance of occurring. The notation, in case you're wondering about this, the probability will be denoted by a capital P, then round brackets. Inside that we will have braces. Okay, these are the curly brackets. It's not very clear. And inside of that we'll have the outcome 1, or the element 1. Right, the probability of event E. Well, event E consists of outcome 2, 4, and 6. Outcomes 2, 4, and 6 are disjoint from each other. If you go back to the section on events, you'll see what disjoint is. It means that they share nothing. 2 is separate from 4, which is separate from 6. They group together, but the actual outcomes themselves share nothing. So we add the probabilities together, so it will be 1 over 6 plus 1 over 6 plus 1 over 6, which gives me my 3 over 6, or 0.5. Probability of getting the outcome 7, well, that's the empty event. In the empty event, we have 0 outcomes over 6, was the relative size, so that gives us 0. Probability of the sample space, we simply add the probabilities for all the outcomes, so we get 6 over 6, which is 1, which is obviously 100%. Probability of the odd numbers union even numbers, so we'll take the probability of the odd numbers, sorry, which is, there's 3 of them, so it's 3 over 6, plus even numbers, there's 3 of them, so that's 3 over 6, and that's going to give us the value 1. Now please take note, I wrote over here, that we can only add probabilities together directly like this if the events are disjoint. And we'll see now why. If we have a probability of A intersection E, intersection is what's being shared. A and E, they're only sharing outcome 2 over there. That's 1 out of a total of 6 outcomes that's being shared. And those 6 outcomes will be the outcomes for the entire sample space. So that gives me 1 over 6, because it's just the probability of outcome 2. Now what about the probability of A union E? Well, A union E will be the sum of A and E. So A will be 3 over 6 and E will be 3 over 6. But now when we add those two together, we get 6 over 6, or we get 1. But that's not possible, because when we add A and E together, we are excluding 5. So that means we can't get 6 over 6. So there's a mistake here. And the mistake is with outcome 2. Outcome 2 is part of event A. So over here, this 3 represents outcomes 1 and 3 and outcome 2. And this 3 over here represents outcomes 4 and 6 and outcome 2 as well. So outcome 2 is being added twice. So we can't have that. So we need to subtract the outcome 2, which is 1 over 6, so that we don't duplicate it. And that is indicated here, right? A and E are not disjoint, so that's why we need to subtract this. And that will give us 5 over 6. Right, for the relative frequency method, we'll go back to the data set that I used in the previous examples. There we have the numbers 0 up to 290 in our table. We sorted this into a frequency table and histogram as well. And in this case, I'm just pretending that it's in the form of a Venn diagram so that it looks pretty much the same as the first one. The probability of event E1, which is this one over here, will be approximately the relative frequency of E1, and that is 1 over 20. Probability of event E3 will be approximately the relative frequency of E3, and that will be 6 over 20, because we have 1, 2, 3, 4, 5, 6 outcomes in there. So it'll be the same for each. Now what about the probability of E1 intersection E2? Well, E1 and E2 are disjoint. They have nothing in common. So that means the probability of this intersection will be approximately the relative frequency of that intersection. So the relative frequency is counting how many outcomes we have in the intersection, and that's 0, and dividing it by the total number of outcomes, which is 20. So that will give us 0. What about the union? Well, it will be approximately the relative frequency of the union. How many elements in the union? Well, 2. There's nothing being shared. They are disjoint, so we can simply add them together to give us 2 over 20. What about the probability of the complement? Remember this little sign over here, that little apostrophe, that means a complement. So probability of E4 complement will be approximately the relative frequency of E4 complement. What is E4? It's this one over here. How many outcomes? 2, 4, 6, 8. Remember, the complement is the opposite. We have 20 in total. So 20 minus 8 gives us 12. So it's 12 over 20 that will be in the complement. Now what about our frequency table? Well, we can find or estimate probabilities from here as well. Probability of being in this interval, 58.5, which is over there, up to 176.5, which is over there. That means these two classes are being added together, so it's 1 plus 6 over 20, and that gives us 0.35. Right? We're adding those two together. What about for histogram? Well, it's exactly the same thing. Probability, let's say, of x greater than 235.5, it's going to be that interval over here, and the probability will be estimated using that area over there, which is 4 over 20. Okay, there's 4, That's the height. And I said in an earlier section that we consider the area as being the probability. Okay, so we're estimating the probability in this case with the relative frequency. And just to remind you that x over there refers to the entire data set. This x over here as well, I used it to refer to the entire data set. Right, so what do we see? We see that for probabilities, the probability stays between 0 and 1. Because if we have an empty event, then it's going to be 0 over 20. If we have the sample space, it's going to be 20 over 20. So we can't have anything outside of that interval. Right, so when we have an event that's on the sample space, then the probability will be between 0 and 1. Probability of the sample space itself will be 1. Probability of the union will be the sum of the probabilities, but only when the events are disjoint. We saw that in the example. And when they are not disjoint, then we need to get rid of the duplicate events or outcomes in the intersection. What about for relative frequency? Well, we have exactly the same results, except now that it's going to be the relative frequencies, still between 0 and 1. Relative frequency of the sample space is still 1. Of the union, we still add when they're disjoint. We have to subtract the intersection when they're not disjoint. So whether it's probability or relative frequency, we have exactly the same properties for both. Right, now the next section looks at the multiplication rule for probability. Now this should ring a bell because we've already looked at the multiplication rule for counting techniques, and this is very much the same. Right, let's consider flipping a coin 3 times, and then this is the outcome that we'll have. Now remember, flipping a coin 3 times, we have 2 sides to a coin, and we're flipping it 3 times, so we're repeating the same thing 3 times. Or we can say that the experiment consists of 3 parts, right? Part 1, part 2, part 3. Each part has 2 possible outcomes, so multiplying them all together, that gives us 8. So here we have our 8 outcomes, 2, 3, 4, 5, 6, 7, 8. And please note that the outcomes are not these last heads and tails over here. The outcomes are dots, and these dots are multivariate because we have 3 things describing the dot. If you're not sure what multivariate is, go back to the section on types of data. So these 3 heads come from this branch over here. So when we reach the end, the outcome of the experiment will be whatever is on that specific branch. Right, so here we have the 8 outcomes, which we've also seen before, and it has multivariate data, okay, because there's 3. Now, it says here a fair coin. So that means the probabilities are equal for heads and tails. So the probability of a head will be a half. So I've filled in probability of a head everywhere where I have a head. Probability of a tail will be a half. So I've filled that in everywhere as well. So now we can look at the probabilities of the branches themselves. In other words, the probabilities of these outcomes. Now it says here all and only possible outcomes, so we have a population. That's really important. There's nothing else that's possible. Okay, so this is definitely a population. So that means capital N will be equal to 8. So if we look at the probabilities of these events, then the principle of indifference says that all outcomes are equal. So that means because we have 8 outcomes, each one will have probability 1 over 8. Now, what does the multiplication rule say? Well, the multiplication rule says simply multiply the probabilities on each branch to get the probability of that outcome represented by that branch. So that means in the first branch over here, I need to multiply a half by a half by a half. And lo and behold, that's equal to 1 over 8. For the second branch, I have a half for heads, a half for heads, and a half for tails. You can see the colors here, pink, pink and green. And lo and behold, it is equal to 1 over 8. So the same thing will hold for all the rest as well. It's going to be a half times a half times a half, which will give us 1 over 8. So the multiplication rule that says multiply it all together gives us the same as the principle of indifference, right? Or the classical method of assigning probabilities. Now, what about the case where we have a biased coin? Now, when we say a biased coin, it means that it's unfair. So in this case, the probability of getting a head will be 1 over 3. Getting a tail will be 2 over 3. We still have the same process. We have the 3 stages, in other words, flipping the coin 3 times. We still have the same outcomes. That's multivariate. We still have a population. But now, when we assign probabilities of heads, it's going to be 1 over 3, 1 over 3 for all of them. When we assign tails, it's going to be 2 over 3 for all of them. Now, the principle of indifference says all outcomes are equal, so the probabilities must be 1 over 8 because this population size is 8. However, now the multiplication rule says multiply it. So it's 1 over 3 times 1 over 3 times 1 over 3. That's 1 over 27. The next one, 1 over 3 times 1 over 3 times 2 over 3. Okay, so it's the 1 over 3, 1 over 3 times 2 over 3 for the next one. And that gives us 2 over 27. Then we carry on in that way. The last two, we get 4 over 27 and 8 over 27. And that's definitely not equal to the 1 over 8s, right? However, we ignore the principle of indifference in this case because these outcomes are not equal. Okay, so we can't use a principle of indifference. Outcomes will only be equal when the process is fair. So then we can use the classical method or the principle of indifference. Here, clearly the outcomes are not equal. So we should rather just use a multiplication rule that will give us our probabilities for the events. Right, so the way in which we'll read this, 1 over 27, means that for every 27 outcomes, one of them will have 3 heads. Like if we repeat the experiment 27 times, okay, and the same for the next one. To get 2 heads and a tail, only 2 out of 27 outcomes will be that. Right, let's look at another example for the multiplication rule. What's the probability of selecting 2 males from a class of 10 males and 10 females? Now it says here the males must be selected in order and with replacement. So we can construct a tree diagram. Selecting 2 males, that means we'll be sitting on the first branch. So these are the 4 outcomes for the experiment. Okay, only 4 possible outcomes, so this again is a population. Now, we're interested in the first one over here. If we look at the probability of selecting a male first, it will be 10 over 20, because I have 10 males in the class out of a total of 20 people. Females will also be 10 over 20, because I have 10 females. In the second stage, the probabilities will still be 10 over 20, because it says here I'm selecting with replacement. So if I select male 1, I might ask him a few questions and put him back into the class, and then randomly select a second person, which could end up being the same person. Right, so the probabilities don't change. So if we use a multiplication rule, then the probability of getting 2 males in that order will be 10 over 20 times 10 over 20. If we look at the other outcomes, then we see that it's exactly the same, because all the branches have probability 10 over 20. Now what is 10 over 20? It's just a half. So we can think of this as almost like flipping a coin 2 times. Now, the way in which we will write it is we will say it's the probability of a male first times the probability of a male second. Right, and then the same over here. Probability of a male first, probability of a female second. We'll multiply those two probabilities together according to the multiplication rule. Now, what about if we still have the same class, but now we're selecting two males in order and without replacement? Okay, without replacement. We still have the same possible outcomes, and we still have the same probabilities to start off with. Male first will be 10 over 20, female first will also be 10 over 20, but now if we remove a male, we're not putting him back. So that means the chances of getting a male the second time round will now be 9 over 19, because one of the 10 is gone and one of the 20 is gone. Getting a female second will be 10 over 19, because I still have the 10 females. That didn't change over here, but I did remove somebody from the population, so that means the population size is now 19. And similarly over here, removing a female first means the males remain the same, but the sample size changed. Females changed and the sample size changed. Now the multiplication rule says just multiply everything on the branch. So it's 10 over 20 times 9 over 19. For the others, you will see that it's exactly the same situation. We just multiply whatever appears on the branches. Right, now something interesting to note that takes us back to the section on counting techniques. If we look at this 10 over 20 times 9 over 19, we would like to see where that actually comes from. Like I said, it's nice to look at this because it relates back to the counting techniques. Now if we use our counting techniques, then we'll start off and we'll say that the probability of getting a male first and a male second will be the number of outcomes in that event, okay, the number in that intersection, divided by the total number in the population. Okay, so that's the outcomes in the event and the outcomes in the sample space. Now how do we calculate the number of outcomes in the event? Well, it's going to be 10 permutation 2. Why permutation? Because it says here selecting in order and without replacement. So that's the condition for a permutation. So we have 10 males, permutation 2. So we have 10 males and we're selecting 2 in order. The size of the sample space, well, the sample space considers all possible selections. So it's going to be 20 permutation 2. Okay, all possible selections of size 2. So we don't care whether it's male or female, so that's why it's the 20. Okay, all possible selections. And to stress, it's in order and without replacement. So if we look at the permutation formula, then this is just going to be 10 factorial over 8 factorial, and this is going to be actually 20 factorial over 18 factorial. Okay, this is 20 factorial over 18 factorial, but I took a shortcut, so I just wrote 20 times 19. And if I do the same with the numerator, it's 10 times 9. So what do you notice? We end up with 10 over 20 times 9 over 19, which is exactly what we have over here from the multiplication rule for probability. Okay, so this in order and without replacement should have reminded you of a permutation. And we can see that the result that we get using the multiplication rule is exactly the same as what we would have gotten for permutations. Right, now, very important. This probability over here is a probability of selecting a male first, so we'll write it in this way. This probability is selecting a male second. However, it's not the same probability as before. It changed. This probability is affected by what happened before. This is 19 because one person was taken from the sample. This is 9 because it was a male. So what we need to do is we need to indicate that. The fact that the sample space is changing means that the previous event has an effect on the next event. So that means we have dependent events. Okay, the second one is dependent on the first. And this is how we denote it. This vertical line over here denotes conditional probability. It means that we calculate the probability of a male second conditioning or given the fact that this happened before. Because whatever happened over here, right, whatever happened first, we need to consider that information when we calculate the probability of a male second. With the previous example where we did with replacement, this was 10 over 20 and that was 10 over 20. So the previous event had no effect on the second, whereas here it does. So we have to indicate it with this vertical line, and then the first event must be after that vertical line, because that indicates some information that will cause the probability to change. Right, so we do the same with the others. This male over here, which should be an M1, has an effect on the female second. This female over here has an effect on the male second, and this female over here has an effect on the female second. Right, so that is conditional probability, where one event is dependent on another, or it is affected by another. Right, so that brings us to the section on conditional probability. Now there's a definition that you have to know. It says that the probability of the intersection of A and B, where A and B can be any two events as long as they're not zero, or rather empty. Probability of the intersection will be the probability of A given B times the probability of B. Okay, so in other words, just the conditional probability of A times the probability of B. Now this should look familiar because it's exactly what we just saw now in the previous example over here. Okay, probability of the one event times the probability of the other that's being affected by the first. Probability of the one event and the other that's being affected by the first. Right, now let's have a look at what that actually means graphically. If we roll the six-sided fair die, we consider these two sample spaces. Okay, we've seen this before. The one on the left will be the probability, or we can calculate the probability of getting the outcome 2 will be 1 over 6, because it's 1 divided by the total, which is 6. But the one on the right, if I say the probability of event 2 or outcome 2, given that an even number has occurred. So the fact that I say that an even number has occurred, it means that you can ignore the odd numbers. An even number has occurred, so the sample space is now reduced to 3. So that means outcome 2 will be one outcome out of a total of 3, so the probability is just 1 over 3. So when we condition, what happens is that the sample space changes. So we first need to identify the new sample space, and then we can calculate our probability in the usual way. Let's have a look at another example. Let's have a look at survey results of 4,000 online shoppers or visitors to a specific shopping website. This was the data that was collected, and out of the 4,000 people, we had 1,039 that doesn't shop online, 2,961 that does shop online. Out of the 4,000, 3,609 were female and 391 were male. Now, if we randomly select a person out of that 4,000, okay, so randomly, remember, we don't know which one we're going to be selecting, then the probability of a female will simply be 3609, okay, which is this over here, 3609, divided by 4,000, because this is the total number of elements in the event of being female, and this is the total number of elements in the sample space. Okay, so we're simply dividing the two. And please take note that this probability should in actual fact, strictly speaking, be approximate. Because these are relative frequencies, it's based on a sample of 4,000 people that visited the website. It's obviously not everybody that has ever visited the website. Right, probability of getting somebody that doesn't shop online, well, that's obviously just going to be 1,039 divided by 4,000. Probability of selecting a male randomly, well, that's just going to be 391, again, divided by 4,000. And the same for selecting somebody that shops online. That's going to be 2961 divided by 4,000. Now, what about the probability of selecting a female if we know that the person shops online? Well, that means we only consider those who shop online. So that means we only consider this row over here. Those are the online shoppers. So my sample space that I'll be using is 2961. I'm interested in selecting a female, and I have 2718 females. So this should be a sample space of 2961 and a numerator of 2718 because I'm only looking at females. According to our definition, this is how we'll calculate it. The intersection. Okay, now this is an intersection, this 2718, because it's the event of a female and the event of online. Just to remind you, you can go back to the section on events where this is explained. And we're dividing it by the number in the online shopping group, which is 2961. Right, so the same for the probability of selecting a male given that the person does not shop online. So that means we're only looking at those who do not shop online, so it's that group over there. Probability of a male will be that value over there divided by the sample size. So it should be 148 over 1039. And the way in which we calculate it by the definition is the same. We'll take the probability of the intersection, male and online, and we'll divide it by the probability of, male and not online, and we'll divide it by the probability of that. Right, and then lastly, probability of not shopping online, given that we have a female. So that means we only look at the females. Total will be 3609, which we have over there, and not shopping online 891, so we'll take 891 divided by 3609. Right, and then the way in which we calculate it using our definition, it will be the probability of the intersection divided by the probability of the event of female. Right, so this is using our definition this way over here. It is a bit longer, but it is the proper way of doing it. So just to show you the detail, probability of this intersection, female and online shopping, will be 2718 divided by 4000 because it's the probability over probability of online shopping, that will be 2961 divided by 4000. So you'll see what happens, the 4000s cancel and we're left with 2718 over 2961, which is exactly this over here. And the same is going to happen with the others. Okay, the sample sizes will cancel out and we're simply left with the numerators because, like I said before, the sample size changes because of something that happened before. Okay, we are conditioning. Right, that brings us to the end of conditional probability and probability. Please note the conditional probability is very important. It comes up again in Bayes' theorem, which is the next section.